Hello everyone, we are here today to record the lecture 7 of the course Automata and Formal Languages, and today we will study unit 6 and we will talk about non-regular languages, and finally we will learn how to prove that the language is non-regular, and we will use the pumping lemma. By the way, we are still using Sipser book and we are still at chapter 1. Okay, let's start with some questions. The first question, are all languages regular? And the answer is definitely no. I showed you several non-regular languages during the classes, and I would like to mention that majority of languages are non-regular. Why? Once again, we already talked about it. We are using finite state machine. We have a finite memory. We can remember something only with the states. Since we are using finite state machine, we have limited memory. Additional question. How do we prove that the language is regular? Here you can build deterministic finite automaton or non-deterministic finite automaton, or you can show a regular expression. How do we show that the language is non-regular? So currently I only mentioned that some languages are non-regular. I showed several examples, but today we will study how to prove that some language is non-regular, and we will use something that is called a pumping lemma. Okay, let's start with an example of automaton of the finite language. If LA is finite, the meaning is that it has finite number of words, and number of states in A is n, then the longest word of L is less than n in length. So if I will put all states together, the maximum length word that I can see is the word of length n. For example, in this example, we see an automaton, non-deterministic automaton, since in Q2 we don't know what to do with 0 and 1. We have 3 states, and the automaton has 3 states. The language of A is all words of length 2 or less. We have the following theorem about finite languages. If L is finite, then L is regular. Okay, if we have L, a finite language, the proof idea will be the following one. L has a finite number of words. We already showed several lectures ago that for each word W in L, we can build an automaton for a single word. So let's say that I've built an automaton for each word in L. Now I add additional Q start state and I go with epsilon transition from Q start to initial state of all the automatons of the single word. The resulting automaton recognizes the language L, therefore we proved the theorem by construction. Okay, let's start talking about infinite languages. Infinite languages can be regular or non-regular. Let's see some example. For example, the first example here, L equals 0 in power of n, 1 in power of m, and n and m are not related and greater than 0. So here we are talking about regular language. We have some prefix of 0 and some suffix of 1. And there is no relation between zeros and 1. The next language will be a non-regular language, and it's written more or less the same, but now we are talking about L equals 0 in power of n, 1 in power of m, but m is greater than 1. So now we would like to have a number of ones greater than the number of zeros in prefix. Now we will have to count. We will have to count how many zeros did we have. So to show that, just to prove the idea, I'm talking about the language that we have prefix of 0, suffix of 1, and the number of ones greater than the number of 0. This language has to be non-regular since when I reach ones, I have to remember how many zeros I had. To remember how many zeros I had, I'm using finite state automaton. I have only finite number of states, so I can remember only finite counter. And now we are talking about language that has infinite number of words. Since the length of the zeros prefixes is not bounded, I can't count it. And I can't compare it with the number of ones that we have later. Therefore, a finite automaton can't accept this language, and that is why this language will be non-regular language. But it's only an idea. I will have to prove this. Let's see some additional examples of infinite languages and automaton for those languages. So I'm talking about regular languages. The language L has prefix of A, B star, C. A, B star, C. So to build this automaton, I use three states. I move from Q0 with A to Q1. In Q1, we have a loop of B's, and we move from Q1 to Q2 with C. So I will rename the path. The path from Q0 to Q1, I will call it X. The self loop in Q1, I will call this part, I will rename this part to Y. And the part from Q1 to Q2 in accepting state, I will call this part Z. So basically, when we are talking about infinite language, we are talking about each word that can be separated for this language in three parts. X, the part that goes from initial state to some state where we have loop. The loop from Q1 to Q1, we called it Y substring, that is actually a loop. And Z, a substring that goes from loop to finite state. Therefore, I can tell that I can separate each word W in L into X, Y, Z, into substring concatenation of substring X, substring Y, and substring Z. Please pay attention that X and Z can be empty, but the loop part need to be non-empty. Therefore, I would like to have at least one edge with a loop. Therefore, we will assume that Y will be never epsilon. So here we see the automaton for the language sigma star. Epsilon actually belongs to sigma star, but we also accept infinite number of words of any structure. The pumping lemma is the central theorem concerning regular languages. We will use the pumping lemma to show that some language is non-regular. The pumping lemma actually determines the basic nature of regular language. Any regular language satisfies the lemma. The language that does not satisfy lemma must be non-regular, and this is the point that we will use to show that some languages are non-regular. The pumping lemma idea. We assume that we have a deterministic finite state automaton with n states. Any word W belonging to L with length greater than n must include a loop. Since I have n state, even if I will build an automaton which is a single line, the maximum word without the loop that I can accept will be the word of length n minus 1. So if I'm choosing the word w with the length greater or equal to n, it must include a loop. We will denote the prefix before the loop by x. We will denote the loop substring as y, and we will denote the suffix or postfix after the loop by z. The z part ends and leads us to an accepting state. Therefore, we are talking about the word w that was accepted by automaton. The loop part can be repeated any number of times. It can be repeated 0 times. It can be repeated 2 times. It can be repeated 4 times until infinity. Therefore, we can claim that we are pumping the word. That is why we are talking about the pumping lemma. So, if we have the prefix that leads to some state R, a loop in R, and then the suffix that leads to the accepting state, the word x, y in power of I, z will also belong to L because we will finish reading the word in an accepting state. And it will be true for any I greater equals to 0. So let's see the formal definition of the pumping lemma. If L is a regular language, then there is a number n such that any string w that belongs to L, where w greater than equals to n, can be divided into 3 parts, x, y, z, such that the length of the y loop part is greater than 0, x and y together, the length of x concatenation y is less than equals to n, and for each I, uh, x, y in power of I, z belongs to L. This lemma is true for a regular language. Each regular language holds those properties. So let's ask some additional questions and let's think about those questions. How can a finite language be regular? We already showed it at the beginning of the lecture. We just built into automaton for each word and then combine it together. Can a finite language include the word w such that the length of w greater equals to n? No, I already answered it. If we have a finite state automaton with n states, the maximum length of the word that we can accept without loops, and in finite language we don't have loops, the maximum length will be n minus 1. Does a finite language satisfy the lemma? No, because we don't have a loop part. So it can't satisfy the lemma because the y part is the length of the y part, the y substring is 0. Can y be the empty word? No, I already mentioned it. Can x be the empty word? Yes, I already showed you an example. How can we prove that a language is not regular? We will use the formal proof where we will use contradiction. We will take some language, assume that it is a regular language. We will try to satisfy those 3 conditions, and we will show that we have some contradiction. Therefore, our assumption that original language was regular would be incorrect. But I will do it several times today. Okay, so let's start with formal proof of the pumping lemma. Let M be a deterministic finite state automaton that recognizes L. Let N be the number of states of M. Let W be the word that belongs to L, and the length of W will be greater or equal to N. The sequence of states in automaton M that we go through when reading W leads from Q0 to some finite states, since we are talking about the word W that was accepted. In this path from Q0 to the finite state, we have at least one state that was repeated. Let's call the state R from the word repeat. Why? Since we are talking about W that having n, the length of n or even more, then if we build an automaton, we will have at least one state that repeated, because without the repetition, the maximum length of the word will be n minus 1. And we started with the word W with length equals to n or even greater to n. So we will call the repeated state R. Let X be the prefix of W that we read from the initial state to the first appearance of R. Let Y be the substring from the first appearance of R till the second appearance of R, and let Z be the suffix of W that we read after the second appearance of R until the end of the word and finite state F. Since the substring Z ends with an accepting state, the word W belongs to L. Y is a loop in the automaton. The length of Y is greater equals to 1, is greater than 0, since we have to use at least one letter to move from R to R. The length of concatenation between prefix X and the loop part Y, the length of this part is less equals to n, since we are talking about the prefix until the first repetition and the substring until the second repetition of R. The path from R to an accepting state F can be a direct path without using any loop. We can go from Q0 to R with the prefix 6, and we can continue with R to F with the suffix Z. Therefore, the word X, Y in power of 0, Z, which is XZ, belongs to L, since we finish reading it in accepting state. But we can also use the loop part as many times as we want. So we can go from Q0 to R. Then we can perform loop from R to R as many times as we want. And then we will continue from R to F. Therefore, the word X, Y in power of Y, Z also belongs to L. And there is no limit on number of times we can use the loop. Therefore, I can be any I, and we managed to prove the theory. So once again, an example on infinite irregular language. We have some path prefix, the loop part, and the suffix part. And we can accept each word of the structure X, Y in power of I, Z, and the word will belong to the language. Another example is sigma star. Here we have an empty prefix and an empty suffix, and X and Z equals epsilon. But we have a loop of the length 1 with letters A and B written over it. Therefore, the y part is not epsilon, not an empty part. If we have a finite language, let's see the previous finite language. Now we have automaton with additional state Q3. Now we are talking about DFA. It has 4 states. The language of L is all words of length 2 or less. So let's see how pumping lemma works here, since we have a loop. But please pay attention. We have a loop that doesn't lead us to an accepting state. We have loop which is actually a trap state. Q3 is a trap state. For finite languages, we have the following theorem. For a DFA, if the language of A, LA, is finite, and the number of states in A is n, then the longest word in L has a length less than n. The maximum length will be n minus 1. If you want to prove this theorem, so please do the following thing. Assume that exists the word W that belongs to L and that the length of W is actually greater or equals to n. Then assume that exists a partition of W to x, y, z such that the parts 1, 2 of 3 and 3 of the pumping lemma exist. Then you will show that since part 1, 2 and 3 of the pumping lemma exist, then your language is infinite. And here you have a contradiction to the beginning of the theorem that talks about LA as a finite language. So basically, the proof here will be the proof by contradiction. I already mentioned it, but the usage of pumping lemma will be not to prove that some language is regular. To prove that some language is regular, you will have to build a finite automaton. It doesn't matter deterministic finite state automaton or non-deterministic finite state automaton, or to show a regular expression. But to prove that some language is non-regular, we will use the pumping lemma. And the technique will be the following one. We will assume that our language is regular. We will assume that exists some n, and we will find the word W such that the length of W will be greater or equal to n. We will show that any partition of W into x, y, z such that holds properties 1 and 2 of pumping lemma. The one part is that the loop is not empty and the x concatenation 1 y is less equal to n. And then we will show some I, that exists some I, that if we are pumping our word and we have the word x, y in power of y, z, then this new word does not belong to L. But according to pumping lemma, it should belong to L. Therefore, we will show that our assumption that the language is not regular is incorrect. So let's do our first example. We are talking about language L that has equal number of zeros and ones, the equal number of zeros in prefix to the ones in suffix. So we are talking about L equals 0 in power of m, 1 in power of m, where m is greater than 0. We will use the pumping lemma to show that the language is not regular. How do we do it? We will assume that L is regular, then let n be the number promised by lemma, and we will take a word W of the following form. 0 in power of n, 1 in power of n. Please remember that n is the number promised by lemma. The word W belongs to L. The word W is larger, the length of the word W is larger than n. And according to pumping lemma, there is a partition of W to x, y, z, satisfying condition 1, 2, and 3 of the lemma. X concatenation 1 should be less than 0. Therefore, in this part we will have only zeros. Let's denote the length of x, the prefix, by s, and the length of loop y by t. X equals to 0 in power of s, larger equal to 0. Y equals to 0 in power of t, where t is definitely greater than 0, and s plus t less equal to n. The suffix part z has all the remaining letters, so we have 0 in power of n minus s minus t, concatenation with 1 in power of n. By pumping lemma, if the language is regular, then x, y in power of I, z belongs to L for any I. We will take I that equals 2, and we will see the resulting word. The word W2 will be x, y in power of 2, z. The x part is 0 in power of s. The y part is z in power of t, and we have the y part twice, so we have z in power of 2t. Then we have z part 0 in power of n minus s minus t, concatenation with 1 in power of n. The resulting string that we have has the following form. The number of zeros in power n plus t, and the number of ones equals to n. Since t is larger than 0, we know that the word doesn't belong to the language, since now we have the number of zeros greater than the number of ones. So the number of zeros in prefix is larger and not equal to the number of ones in suffix. Therefore, we have a word that doesn't belong to L. And this is a contradiction to the pumping lemma. So our assumption that L was a regular language was wrong. Therefore, we managed to prove that the language L is non-regular. Let's take another example. L equals to 0 in power of m, 1 in power of n, and m is larger than n. So we have the number of zeros in prefix larger than the number of ones in suffix. Let's assume that L is regular. Let P will be the number promised by lemma. We don't have all the time to write n. Let's choose the word W that equals to 0 in power P plus 1, 1 in power of P. So we have at least one more zeros in prefix. The word W belongs to L. The word W has length greater than P. W can be split into parts x, y, z, such that x, y together less equal to P, and the y part, the length of the y part, is not 0. Since x concatenation 1, the length of this part is less equal to P, we know that this part is written only with zeros. So we will choose I, promised by lemma, the third property, I equal 0. And we will look at word W0, which is x, y in power of 0, z. Since the number of zeros in W0 is P plus 1 minus S, where S is the length of the loop part, the Y part, and S is greater than 1, then we know that the number of ones in W0 is P. So now, since S greater than 0, we know that the number of zeros in W0 is less or equal to number of 1 in W0s, but not greater. Therefore, we manage to delete some zeros, and the word W0 does not belong to the language. But according to the pumping lemma, it should belong to the language. Therefore, our assumption that L is regular is not correct, and L is non-regular language. Additional language that we will show during our practice exercise. L equals to 0 in power of m, 1 in power of n. M is less than n. So basically it will be the same proof, but we will increase the number of zeros. Therefore, we will finally reach the word, or we will have the word that does not belong to the language. Okay, let's solve another example. We are talking about language L that has a in power of k factorial, where k is any number, k is greater equals to 0. Our claim that L is non-regular. We will once again assume the contrary, and we will assume that L is regular. Let n be the number promised by the pumping lemma. We choose the word W. W equals to a in power of n factorial, where n will be maximum between n and 2. The word W belongs to L. The word W is greater, the length of the word W is greater than n. So, by the pumping lemma, W can be divided into 3 parts, x, y, z, such that x and y together are less than equal to n. X and y together consist only of s. Let's denote the length of x by s, the length of y by t. S greater equals to 0, t greater than 0, s and t together less equal to n. And the z part, we have all the rest, the suffix of the word. And in suffix, we have a in power of n factorial minus t minus s. According to the third property of the pumping lemma, the word x, y in power of I, z should belong to the language L for any I. Let's choose I equals to 2. The word W2, x, y in power of 2z, is actually a in power of n factorial plus t, where t is greater than 0. We know that t is greater than 0 but less equals to n, which means that n factorial plus t is less than or equal to n factorial plus n, which is definitely less than n factorial plus n minus 1, which is definitely less than n factorial plus is replaced with multiplication, n factorial multiplication n plus 1, which is, according to the definition of factorial, is n plus 1 factorial. Therefore, we know that the word W2 is definitely has the length less than n plus 1 factorial. Therefore, the word W2 does not belong to the language, which is a contradiction to the third property of the lemma. Therefore, our assumption that L is a regular language is incorrect, and L is non-regular. Okay, additional language which is not regular. L, where we have WW, where W belongs to alphabet 0, 1, a star. We claim that L is not regular. We once again will use the pumping lemma, but we will do it in class, and here you even showed the words that we will use. I would like to talk about some keywords that you should take into account. The lemma claimed the following part. If L is regular, exists N such that any word W such that the word belongs to L and the length of the word is greater or equal to N, can be divided into three parts, X, Y, and Z, such that the word and the partition hold properties 1, 2, and 3 of lemma. That doesn't the meaning of the lemma. If the language is regular, it should hold the lemma. If we proved that lemma does not work, we proved that the language is non-regular. But if the lemma works for some language, it doesn't mean that the language is regular. The language still can be not regular language. To show that the language is regular, you have to build finite state automaton, doesn't matter deterministic or non-deterministic, or regular expression. In order to show that L is non-regular, you have to show that there is N and exists the word W such that for all different partitions of W to X, Y, and Z, or the first property of the lemma does not work, or the second or the third does not work. So please pay attention. If the language is regular, then exist N such for all words W, exist partition that holds 1, 2, 3. But if the language is non-regular, then you have to show that for every N exists W, such that W belongs to the language and the length of W greater equal to N, such that for all partitions of W to X, Y, Z, you have a contradiction or to first, or to second, or to third property of the pumping lemma. Okay, so I would like to mention common mistakes that we sometimes find in your proof. Sometimes you show that for all word W with a length greater equal to 0, lemma is correct for a word W. Therefore, you assume that the language is regular. No, we don't use this lemma to show that the language is regular. To show that the language is regular, once again, you should build or an automaton or regular expression. Sometimes you write exists the word W such that the length of W greater than N and exists some partition of W to X, Y, Z such that X, Y in power of I, Z does not belong to L. Therefore, you proved that the language is not regular. Yes, but you must show it for all possible decompositions of word W to X, Y, Z. Not exists. Additional common mistake. You show that exists the word W, and for all decompositions of W to X, Y, Z, X, Y in power of Z does not belong to L, therefore the language is not regular. But please pay attention. Here, nobody mentioned that the word W that was chosen has length greater equal to n, and it should have the length greater equal to n. So don't do those mistakes, please. Sometimes I can prove that the language is non-regular by using regular closures. So I will have some language that will be non-regular language, but I will assume that it is a regular language. I will use it with some additional regular language, and I will use one of the operations that we showed that regular languages are closed under those operations. But as a result, we will have a non-regular language. Therefore, our assumption that original language L would be, once again, not correct. Let's see an example. We have a language L of the word W, where the number of ones in W equals to the number of 0 in W. And we don't have any information about W structure. Ones can be in prefix and suffix, it doesn't matter. L is not regular. We will assume that L is regular, and since that we know that regular languages are closed under intersection operation, we will do an intersection between regular language 0 star 1 star, very simple automaton, intersection with our language L. The resulting language should be regular language, since regular languages are closed under intersection. The resulting language L cap that we have here is actually 0 in power of n, 1 in power of n for any n. And we know that this language is not regular. We already showed it. Therefore, our assumption that original language L was regular is not correct. Therefore, L is non-regular. Our next language will be L equals to 0 in power of s, 1 in power of t. S is not equal to t. Here, once again, we will use regular operations to show that this language is non-regular, but we will do it during our practice Zoom meeting. Okay, so let's talk a little bit more about regular languages. To prove that the language is regular, you can build DFA or NFA, or you can build a regular expression. To prove that the language is not regular, you usually will use the pumping lemma, and you will show that the language does not hold or does not satisfy all the conditions of the pumping lemma. So once again, to show that the language is not regular, usually we will use the pumping lemma. Okay, basically we finished the first part of the course. We finished talking about regular languages. So let's recap what we did. We talked about finite automata and its 5 tuple, where we have Q, set of states, sigma, alphabet, delta, transition function, Q0, the initial state, and F, finite states. We talked about regular languages. We talked about closure operation over regular languages. And we talked about union, intersection, complement, concatenation, minus, and clean star, the operation, the star operation. We talked about non-deterministic finite automaton, where we can use epsilon transition and where we can also move from one state to several states, or even we can have undefined transition for some letter. We showed equivalence between deterministic finite state automaton and non-deterministic finite automaton, and we showed this both ways. We talked about regular expression, how do you write a regular expression, how you transfer DFA to regular expression, and how you transfer regular expression to DFA. We talked about equivalent states and how do you build minimal states DFA. And today we talked about how do you show that some language is not regular. And usually we will use the pumping lemma to show that some language is not regular. Thank you for listening. We reached the end of Unit 6. Next week we will start learn new models and we will start talking about push-down automaton and grammars, and then we will move to Turing machines. So thank you very much. I will see you during our Zoom practice meeting.